Welcome to the GMI Zener versus Isolated Barriers webinar. Bob, let's start the presentation. We have collected several of your questions during the registration, and we will answer those at the end of the presentation. At the same time, you have the ability to ask questions throughout the webinar. There's a question and answer box, and you can use that. We will answer the question as we can. Let me see if I have control now. Looks like it. So let me take a few moments to introduce Bob. For those of you who have not met him, Bob, our guest, is a speaker today. Has over 30 years of experience in the EX world and is a Comp EX instructor and an instructor for ICEX Comp PC scheme. He's also an inspector and a member of the US ULSTP committee, if I get it all right, Bob.
Yeah, you're doing great.
And this means that he is very, very, very qualified to run this webinar. Before we start, let me take a few moments because I have to. Okay, let's see if I can manage it. Okay, to introduce GMI, what we do, why we do it, and who we are. Basically, GM International is a designer, engineer, is a company designing, engineering, manufacturing intrinsically safe and seal certified interfaces, which we use in all the automation packages from DCS, ESD to SCADA, and marine application, in all the industrial sector, from oil and gas to petrochemical, food and beverage. We have over 40 years of experience, and we are very proud to design, manufacture, engineer all of our products here in Italy, in our headquarters near Milano. We are, on the other hand, a global player with presence around the globe, as we'll see in a little bit. Okay, because we make safety product, safety is important and imperative for us. So we try to do, to put a lot of attention to the quality of our product. We use in state-of-the-art technology, some patent designs. We have 100% product traceability. We have 100% testing on every single component. We have an automated manufacturing process. And of course, we are ROS and REACH compliant and all the other compliant we have to be. Today, it's a very tough word and we have to comply to many, many laws, which we do too. Then we are also SC3 certified. So we have a functional safety management certification up to C3 from 2. These are the products we manufacture. So we go from IS Barriers, safety relays, isolators, also seal certified. We have power supplies, we have multiplexers, termination boards, HART multiplexer, surge protection device, SPDs. We have loop indicators, and we have a division who's providing functional safety training and services. Well, it's too early this morning. We are heading as soon as we were planning to do this in 2020, but you know the COVID has postponed some of our plans. We will do next year for sure. Add an EX competency program to our training division with the help of Bob. We are present around the globe directly through 8, in fact today 9 subsidiaries. We just started a new venture in Australia a few days ago. And we have many distributors, about 200 people. We were running many, many seminars around the globe. Now we are doing webinars. We'll see what's going to happen after the holidays. And we have thousands of installations around the globe. This is some of our customers. We basically interface most, if not all, the system vendors from ABB to Yokogawa. We operate with many, many projects with different EPCs around the globe. We have a series of OEM which we supply to, from Schlumberger to Carrig to Siemens Turbo Machinery. And we are on the AVL of many, many oil and gas companies. Oh, well, today I ran it quite fast. Oh, good. So let me hand you over control once again. Give up remote control. Okay, now you are in control. So as I said earlier, please, any question, just use the question and answer box there and we will try to get to it. I will try to manage it. If I disappear, it's just because I'm, managing the question and answer. So I'm not going anywhere.
Don't go too far away,
Yours.
Paulo. It's very early in the morning, so I don't know exactly what I'm going to be saying. So
you're doing great.
All right.
This is not the first time, so you'll be okay.
All right. Well, let's start off. And by the way, for any of you, and I see that we have some pre-registered people from North America, so I commend you for if you're actually there participating in this at midnight. So that's fantastic. So let's start off a little bit about just hazardous areas and what constitutes a hazardous area. So what is a hazardous area? It's a combination of flammable substances, in this case gases, a combination of oxygen and a source of ignition that can create an explosion. And that material can be a gas, vapor, or dust. Typically refineries or offshore oil platforms are gas hazards, vapors. Dust might be grain elevators, those types of applications. And since oxygen is always present, the only way to avoid ignitions is to control the ignition source caused by the electrical apparatus. So the EN standards and the IEC standards define what are potential ignition sources, and those ignition sources that we typically think of from electrical equipment is generally arcing and sparking devices. But we also actually within the standards have to take into account a bunch of other ignition sources, just anything from exothermic reactions to friction to, well, there's quite a few. But anyway, we have to be aware of the ignition source, and when we have that ignition source with a proper combination of air/oxygen and a gas, then we're going to have an explosion. So the protection methods that we typically talk about and that we use, and this is really true around the world, even though I am here in the United States, and many installations here in the United States, we follow the division concept, which is slightly different than what other people in other parts of the world do, but it's very similar in concept. So where we talk about EXD flame-proof in the international community, in the United States, we typically refer to that as explosion-proof. Intrinsic safety is a protection concept that we've been using here in the United States for many years now. And it's very similar in the design and the concept of how we use it here in the United States as opposed to the rest of the world. But basically what we're trying to do with the ignition triangle, we're either segregating it, and segregation is taking things like encapsulating it, like taking something which is called EXM, and we're putting a resin. We could oil immerse a potential arcing component. We also could pressurize it, so we're using a pressurized enclosure. So we're removing one of the legs of that triangle. In this case, we're basically removing, in effect, that arc or spark away from, in effect, the flammable atmosphere. Containment is basically flame-proof or explosion-proof, where we basically assume we're going to have all three legs of that triangle, but the design of a flame-proof box is such to where it'll contain that explosion safely, allow that hot flaming gas to escape via the flanges, via the thread paths or the flame paths. And then, of course, prevention is really increased safety and intrinsic safety. So increased safety deals with creepage and clearance requirements for energized components, where we have to maintain certain distances between individual circuits. And we do that to make sure that there's no arcing or sparking by the use of special terminals or other devices. And then, of course, intrinsic safety is also a prevention technique. And here we're talking about basically keeping the amount of energy below the ignition curves of the particular gases and vapors. So these are our three main concepts: segregation, containment, and prevention. So obviously we're here talking about intrinsic safety, although I think we have some questions about some other protection techniques that if we have some time, we'll spend some time on. But intrinsic safety is one of the most flexible and cost-effective solutions, and it has been around for many, many years. The original IS devices were developed in the mining industry back in the early 1900s for signaling devices. And under the ATEX directive, that it does a specified device must be connected between the power source and the field device to make the system safe. So this unit is called an intrinsically safe barrier or just barrier. So an intrinsically safe circuit, in effect, is a combination of your field device, could be a simple apparatus, your cables, your associated apparatus, which is what we also use as a term for intrinsically safe barrier, and our control room instrumentation of some sort. So that is what is considered to be our loop, and that's a system concept. So what is it? Again, it's prevention. The characteristics are low power applications. Generally speaking, when we're talking about intrinsic safety, we're talking about effective amount of power of about 1 watt or less. So we've had questions. We had a question in one of the last seminars about, basically making motor starters suitable for IS. And unfortunately, you really just can't do that. Anytime when we start getting into any higher power type applications, we really just cannot use intrinsic safety. So it's really low power applications. There are safety factors built in. So when we actually get into the design of IS systems, we have safety factors that are built in. There's also requirement for isolation distances between IS and also IS and non-IS. And of course, as we mentioned, we also need that barrier. The applications are pretty much your electronic instruments, your measurement and control processes, your battery supply devices. Your 4 to 20 milliamp type transmitters, those thermocouples, solenoid valves, all of the instrumentation, the measuring devices that we typically find in a process facility is really ideal for the use of intrinsic safety. So there's, again, that loop, what we talk about. And actually, when we talk about all the protection concepts, when we teach Compex or when we talk about the IECEX COPC program, actually, one of the things that surprises people, of all the protection concepts, IS is the one where we're actually, it's a true system concept. As I mentioned, we have to take into account the simple apparatus or the IS apparatus, our interconnecting cable, our associated apparatus, and our control room that's providing the power into the system. All the other protection concepts that we really talk about, including EXD, EXP, EXE, they're all basically standalone type protection devices or concepts. And generally speaking, they're all really mechanical protection concepts, where intrinsic safety is a true electrical concept. So with our associated apparatus, there are basically 2 different designs, 2 different concepts, but they're both basically considered to be associated apparatus. One is the Zener barriers. We typically call these barriers. They're passive devices that use Zener diodes to divert any fault current to ground. The other concept is to use isolated barriers or isolators. And these are active instruments that use some sort of safety isolation, typically a transformer or optocouplers to keep a fault energy to pass from a safe to a hazardous location. People use the term barriers and isolators. Again, associated apparatus is kind of the official term, if you will. Some people will call isolated barriers barriers as well, but basically Zener barriers and isolated barriers are the 2 main types of products that you'll find in the marketplace. So when we talk about the protection concepts, there are some advantages and disadvantages, certainly, with intrinsic safety versus flame-proof, explosion-proof, purging, or pressurizing. Basically, if we look at flame-proof or explosion-proof as kind of the median, if you will, intrinsic safety has an extremely high safety record. It is very flexible. Also, the installation cost can be less, and the maintenance cost can be less, okay? I hate saying in generalities because there's always exceptions to the rules, but in generalities, intrinsic safety, when it's applied properly, can be very cost effective. Purging and pressurizing is also very safe. It's also very flexible. There is sometimes a significant installation cost because now we have to deal with ductwork in providing air to a panel. And maintenance cost is about the same as flame-proof. So these are, again, some generalities. It doesn't apply for all installations, but just some of the most common. So Paulo, if you're
All
there,
right.
we have a full
Well, I
question.
want to make sure that, you know, none of you guys are asleep. I was not asleep.
Good.
So we are going to ask you a question. We're going to launch a poll here, and you can answer this simple question. What is the basic protection principle of intrinsic safety? Isolation, mitigation, segregation, prevention, or containment? Well, there is one of the answer is kind of misleading, but let's see, we give you a few moments. I see you're awake because I can see answer coming in. Good. I also see question and answer coming in. Let's see what we got. Oh, okay. I will dismiss arrow answer because that will give it away. Because he actually typed in the correct answer. What is plus, equal, minus in the slide 18? Okay, what we meant in slide 18 was we're trying to say, okay, what is plus meaning benefit, minus being, you know, what is the opposite of benefit?
Detriment.
A detriment,
Negative.
okay. A negative, right? Answer live, okay.
So
all
yeah,
right. I think, wait, let me go back to the end poll. I share the results. So what do you think, Bob?
yeah. I mean, when we talked about it, what did we say? I think we said, I have to find it now. Well, I had it in.
Well, anyhow, we said that it is a prevention method.
That's correct.
So we're trying to prevent versus containment, you know, like EXD box, you are allowing an explosion to happen and you're trying to contain it. Which,
right.
You know, by the way, Bob, I personally think is crazy. But my personal opinion. There are ways, sometimes the only way to manage, you know, hazardous location, but it's
sure,
you're running.
Sure.
Whereas IS is a prevention method. Well, I'd say 50% of you answer correctly, so maybe you have to listen more carefully this morning. We can stop here. Let's move forward.
All right.
Okay.
So a little bit about isolators and Zener barriers and what the principles are. So we realize that some of you may be very familiar with IS. So, you know, some of this may be a repeat and all that good stuff. But for those of you who are not familiar, there are some fundamental differences on the design and the construction of Zener barriers versus isolators. But basically are made up of these components here. And I need to move this little thing out of my way so you, hopefully you can see my mouse.
Yeah,
but
we can, Bob.
You can? Okay.
Okay.
So we have a Zener protecting fuse right here. We have voltage limiting Zener diodes located right here. And we have a current limiting resistor right here. So basically, if we have a fault, right, that fuse, if the current obviously goes way too high, it could potentially blow. That current limiting resistor is going to limit the amount of power. But what's going to happen is the voltage goes up, the fault current, these Zener diodes will basically open up, and any of that excess voltage should be then at that point shunted to a system ground. Here's the important thing to know about your system ground. Excuse me, you have to have 1 ohm resistance maximum on your intrinsically safe earth. Now, also mind you that this is a separate system ground from our normal ground, okay? This is one of the biggest faults, and we do a presentation, we did a webinar here on some of the common faults on the use of IS, and not having a good system. Clean earth is usually one of the biggest problems that we find when I do inspections, is that we don't actually have a good clean earth. Because if we don't have a good clean earth, then all of a sudden there's nothing there to be able to shunt it to. We have all different kinds of problems. But this is the concept of a Zener barrier. Now we look at a isolated barrier, galvanically isolated barrier, and what's basically different. Again, we have our fuse. In this case, we have a current limiting resistor. We also have voltage limiting Zener diodes, but we've also introduced a safety transformer. So what actually happens in a scenario like this, if we have a fault condition that's generated in the safe area that's traveling down this loop, it will hit this transformer and basically stay in effect in the safe area. So that safety transformer is basically taking a signal, replicating it, and sending it on down the line. Notice that there is no requirement for a safety ground the moment that we use isolated barriers. Galvanically isolated barriers basically allow you to use barriers without having a dedicated earth. That's probably the major advantage of using a galvanically isolated product versus a Zener barrier product. So when we have a Zener barrier under a fault condition, as I just mentioned in that other slide, if we did have a fault, we could potentially have this fault come down. Again, if we don't have a good ground connection, it could travel into the hazardous area. Or if we have this ground that's tied in over here, we potentially could have a fault condition in a hazardous area that allows a lot more current into that hazardous area, potentially arcing and sparking, thereby resulting in a bang. So we don't want to see that. Again, the similar scenario using a galvanically isolated barrier, that fault condition stays within the hazardous or non-hazardous area, so it's not transmitted through the safety transformer. Now, the other thing, and this is a question that's come up a couple times, and I think we have a couple questions on this from this webinar that people have asked questions on, the Zener barriers grounding. What is good recommended practice when we are using Zener barriers, and what is typically done? If you notice here, we actually have two grounds. We actually have a safety ground connection, again, 1 ohm max, and we have a redundant safety ground. The reason why we actually have, as good engineering practice, a redundant ground is that periodically we're actually supposed to check to see whether or not this ground loop still has 1 ohm of resistance or less maximum. So the only way that we can check that is that we have to disconnect it from the barrier, because obviously if the barrier is providing protection into the hazardous area, we don't want to do that test while the barrier is actually connected to that intrinsically safe earth. So we have basically a redundant safety ground. Okay, so it's not uncommon. This is not a requirement within the standards, but it's good recommended engineering practice.
Oh, and yes, I interrupt you a second. Yesterday we had a discussion with the customer in it was in South America, but they were saying that they need to test this ground every 6 months. I don't know whether that is a requirement or.
No, so every standard says, so the IEC standard for IS, there is 60079-14 and 60079-25. And basically what the 14 standard says, and I believe 25 says the same thing, is that it should be tested periodically. Okay. Now, if somebody is saying,
their practice to do it every 6 months, probably.
Yeah, that very well could be a situation where a client or maybe a country-specific standard or some regulation in that particular country could say you must test it every 6 months. Now, quite honestly, I have not seen that, and it's very unlikely that people are going to be testing the quality of the ground every 6 months. But if that's a requirement,
an expensive exercise.
That would be something that would be pretty onerous to have to do.
All right.
And by the way, the size of the grounding conductor, generally speaking, if you're using two safety grounds, like what you're doing here, in the IEC world, based upon -14, it says that that minimum conductor must be 1.5 millimeter. If we're only using a single ground, then it must be at least a 4 millimeter. And it may have to be larger in order to achieve that 1 ohm resistance or less.
When you are talking about these numbers, you're referring to which North American standards are we talking about?
That's the IEC standard. That's the -14.
Yes. In the USA, instead, what standard are they typically applying?
So we follow the National Electric Code, the NEC, and it's in Article 504. Yes, 505 is the zone concept. Article 504 is for installations of the IS. And what that translates into AWG, I don't remember right now.
It's okay.
But it is within the NEC. And the CEC also has a similar type passage within the Canadian Electric Code. So here's again a scenario that we could see if we had a fault condition in the hazardous area that could potentially work its way up through the barrier and back into the device. So again, we want to make sure the key thing to remember when we're using Zener diode barriers is that we have to make sure that our structural ground is separate from our clean earth. It must be a separate earth. That's the important thing to remember. So a couple pros and cons, because I know this is always a question that people have. As I mentioned, the galvanically isolated barrier, there is not that grounding requirement. So therefore it can reduce the cost. Accuracy, the installation cost, and again, installation cost has to deal with, well, now I don't have to worry about how I'm going to tie a ground into it, or if I've got an energized bus system, or however I'm going to do it. It also allows the use of a grounded or poorly isolated sensors. This is an issue when you have a lot of noise or some potential issues, right? Zener diodes, probably the biggest advantage of Zener diodes is the cost. And when I say cost, that's typically the initial purchase price. Zener diodes have typically been very inexpensive, and generally they are less expensive than a galvanically isolated barrier. Although I would say this, over the years, really in the last 5 to 10 years, the cost differential between a galvanically isolated product and a Zener barrier is becoming less and less.
And Bob, let me interrupt you for a second. You know, just last night, before I went home, we had a Teams meeting with a big customer, not name it, a very large customer. We are discussing applications, and he mentioned, you know, 4 or 5 Zener barrier model that he's using, and he wants to convert. I was worried about the price, so we had proposed some pricing, and in the end I said, okay, are the pricing okay? And wow, the cost was very in line, basically the same.
Yeah.
The cost, because when you're talking, for example, on in this specific application, there are 2 wires, both requiring Zener barrier on each wire, and in fact, the cost was higher than the isolated barrier.
Right. The other
South American customer, you know, same we were discussing yesterday about the 6 months testing.
Right. The other general big advantage that Zener barriers had over galvanically isolated products was the physical size. You would typically be able to condense a lot more Zener barriers in a cabinet than you could galvanically isolated products. However, manufacturers have gotten better about that, and GMI has done a really nice job of packaging of some of their latest generation to where now the density of a lot of these galvanically isolated products can meet or even exceed, in some cases, the traditional Zener products. So that was usually a big advantage of Zener diode type products, because the footprint could be actually significantly less, but that advantage has kind of gone away with the development of some of the new products.
All right, so now let's see if you guys are still with us. Let me get to the right point, because I was looking at the question, I've been typing up. Okay, I launched this for, be careful before you answer, okay? Read the question correctly. Is a dedicated and low resistance ground required in a galvanically isolated barrier installation? While you guys answer this poll, we got a question, and I'd like to answer this. We answered this last webinar, but can we use galvanically isolated transformer instead of an IS transformer? Well, no. A transformer that is used in an IS barrier, it's not just a transformer. You know, it's called an infallible component. It's a certified component, goes through very rigorous design, manufacturing, and testing. You cannot just take a transformer like you buy one of those, you know, phone charger. Some of them have a transformer in there, but, you know, they melt after a few hours. You put them in the plug. So no, it is when you're talking about safety barriers or safety or intrinsic safety, every component has to be certified. All right, I did answer this. So I think we can end the poll. I can, well, you're still answering. Well, let's take a few more minutes. Done. Okay, well, that's it. Most of you guys got it correct. This time you've been listening. Last time, a lot of people got it wrong. This time you got it correct. It is not required because we're talking about an isolated barrier. So grounding or a special ground is required only for Zener barriers. Okay, Bob, let me go back. Okay, you don't see this anymore, right? Oh, so we are at the end here. Okay, very good.
Yeah.
What happened here? We have another poll? Oh, we went too far?
No. We did that. So.
Oh, okay, sorry, you went for, okay. So why don't you show the next slide? Because I've been reprehended about that. Okay, so because you can, this webinar is recorded, so you guys see our content. Okay, you stop sharing and I will start the question and answer session. Let me get to we have prepared some answers to questions that have been posed during registration. Let me try to share the right presentation in 1 second. Have I got it right?
Yes.
Yes, okay, good. Okay, well, okay, I'll try to run that while I'm checking the answer coming live. So let's see if we can manage. Okay, so the first question, which was, please explain about entity concept and give some example. So Bob, I prepared an answer a little different than last time we talked because we had a similar question.
Let's see what you've come up with.
But in general, you can start introducing the concept. You talked about that earlier. Let's define a little better.
So yeah, what we're talking about, again, when we use intrinsic safety, we have to look at the entire loop of the system. And actually, this is another issue that a lot of people, so when I do inspections, when I go out and I'm contracted out to do inspections and I come across intrinsic safety, one of the first things I'll ask is the client to provide me what is called a descriptive system document, or a DSD, or a loop diagram, or whatever you want to call it. And and sometimes I'll get the blank stare. People look and they say, hey, I don't even know what you're talking about. Well, the reason why we need to have that information is that we have to take into account the entities of the various devices. So our associated apparatus, our cable, our field devices, we need to take all of that into consideration. So basically, is the barrier in compliance with the area classification? Is the field device compliant? Are the safety parameters, they must match, right? Or we must be lower than or equal to, or what have you. And then the cable parameters. And this is the one thing, the cable parameters people forget about, but cable will store energy, right?
In fact, we have a question that came on here just now. You can answer, through this presentation while you're discussing. If the cable parameters, we have to consider core to shield or core to cable capacitance.
That's an interesting.
Let's first discuss about the capacitance of the cable.
Right. So yeah, to answer or to talk further about that, what people fail to remember is that the difference, if we go back, Paulo, one slide.
Yeah.
Go back to the previous slide. There we go. So remember, there's different devices. There's what is called a simple device, right? These do not require certification, and basically how we can determine these is if they don't generate or store energy in excess of those numbers, then that's a simple device. So a switch, simple semiconductor, a thermocouple, an RTD, these are simple devices. The IS apparatus that requires certification, these are items that can store energy. So things like transmitters, valves, proximities, those are all energy storing devices. Well, again, as we mentioned about cable, we have to take into account the cable parameters and the capacitance of the energy storing of the individual core conductors. Now, the question when we do IS calculations, do we consider the core to shield cable capacitance, or do we consider core-to-core cable capacitance? That's an interesting question. I think it's the core-to-core cable capacitance, not necessarily the core-to-shield. But what I will do is that we will take that and answer that question offline. We'll send out, which by the way, we had another question as far as, will you get a copy of this presentation? Yes, I think Paulo will send a copy of this.
Yeah, we sent our presentation to all registered. Do you remember we discussed about cable capacity last time? We had a similar question.
Yeah, it was
I asked my friend, the manufacturer of cabling, about capacitance. The shield, if I remember correctly, increases the capacitance of the cable, right?
It does increase the capacitance. Yes.
So when I believe the numbers you have to use is the one specified by the manufacturer. The manufacturer will give you the maximum capacitance per meter or per feet or per kilometers.
Right.
You just enter that data.
I'll give you an example. We did a project with a client here not too terribly long ago, and based upon the gas group, and this happened to be a 2C gas, which included hydrogen. So it was one of the most onerous applications. And hydrogen has a very low ignition energy. So basically, the amount of capacitance is limited. It's very, very small. So therefore, the cable length had to be extremely short. And what we actually found was that for about 90% of their runs, that cable length was fine. But in about 10% of their cable runs, they exceeded the maximum parameters of what was allowed with regards to the cable. So the solution, if you will, was to move, in effect, the barriers actually closer to the devices in the field to shorten that length. And so the barriers that they were using, they were GMI products, are rated for zone 2 to be installed actually in a zone 2 area. So that is actually something that if you ever ran into that situation where that cable length between the associated apparatus and your field device, you find out is just too long based upon the gas group, then you can certainly, that's one potential solution.
And in fact, we have a couple of questions regarding this, which we have prepared answer to.
Okay.
So basically, guys, you have to, check the parameters, and let's see if I can move forward like this. It sounds complicated. It looks complicated. You got a lot of parameters to check. So the basic concept is somebody posed the question earlier. A barrier is there to limit the energy going into the hazardous location within the curves that are, defined in the standard. There are a maximum allowed energy. In fact, not at the limit of the curves, but 50%, below. There's safety margin built in. But at the same time, the associated apparatus, the apparatus in the field, so your transmitter, it is certified to be installed in a certain location within a given parameter. So basically, if it says the UE of the transmitter is, say, 30 volt, it means that that transmitter has been tested and certified to operate at maximum 30 volt. So what the barrier is there for, to guarantee you don't give it more than 30 volt. And this is true for current, capacitance, inductance. So it can get complicated. So we have prepared online a tool that allows you to do this check easily. And as I was asked a question, I prepared a few samples of the tools, and you can see the result here. And I have outlined here, Bob, different gas group, because a gas group does make a difference in the cabling, as you mentioned. So for example, this is a pressure transmitter example, a real example. It was made a while ago. I didn't make it yesterday. So the transmitter here that I use is an old transmitter, but there are actual data. You enter the data of your barrier, and the tool automatically uploads those. You enter the data of your transmitter, And the tool is telling you if it is, and then of course you have to enter the data of the cable, and the cable, depends on the quality of the cable you use. The cheaper cable typically have, worse parameters. Anyhow, you can see that if I select gas group second C, so hydrogen, my maximum distance in this application is 700 meters, which is a long distance. But still, if I use second, what did I choose here? Second B.
Second B.
Second B, you can go a lot further. The same is, here I made a different example on DI switch between a simple device. So a switch, which you can see on the right side, which has no safety parameter, and the only one you look for are the cabling, and an Amur switch, which does have safety parameter. And you see the difference is basically nil, not applicable, because the safety parameter of a DI switch are basically very, very small. There's no capacitance and no inductance in the switch. It's just a switch.
It's just a switch, no stored energy.
Yeah, but then there was a question regarding solenoid valves, so I put this example in there. You can see the big difference here between a second C and a second B. When the energy you can provide in second C is a lot less than in second B, and then you have also 2A, right? So we will share the copy of the presentation, and you will be able to look into this and eventually go online, download the tools, and do your own calculations. I think we answered that, right, Bob?
I think so.
Let's move forward because timing is not on our favor. So the next answer we got online was IS Isolators Zener Barriers. It's just matter of grounding, cost, pros and cons. It's basically a summary of what we discussed earlier, but we can go through a little bit again. What are the differences?
Yeah, I think we've covered most of this. Again, typically in favor of the Zener barrier when we're just talking a cost comparison. But the CapEx usually makes it more expensive. Zeners do the independent ground. The multi-channel isolated barriers typically will cost less than the Zener barriers. There's more, I would say, and Paulo, is this true? I mean, I've seen much more multi-channel products in the isolator type products where we can do up to 8 channels in a single housing, if you will, that I really haven't seen those in the Zener barrier world. Is that?
Zener barriers, they're not available, but in reality, in the real world of safety, not many people use multi-channel isolators because they're concerned about single channel integrity. Although you still have single channel integrity. We were just discussing this yesterday, with this customer. And I said, okay, well, if you use dual channel, you have actually 6 millimeters per channel. So it's actually a lot less dense than a Zener barrier. And he says, okay, but if I drop one channel, I drop both channels. I said, no, they're independent. But what will happen is when you need to replace, in case of replacement, of course, you have to disconnect 2 channels instead of a single channel. So it's because of this issue, I find it quite interesting discussion, because we're interfacing with PLC, which have 32 channel DI cards, but anyhow. We have a lot of live questions here. Let's see if we can answer some of this. To power IS instrument, do we require IS power supply, or it can be powered using normal power supply? In between an IS barrier. The barrier itself can be powered by normal power supply, right?
Correct. Right.
But you cannot send a power into the hazardous location with a normal power supply. So
that's correct. Now, for example, I mean, you do GMI makes power supplies that are IS, that have incorporated intrinsic safety into them. But to utilize a normal power supply beyond the barrier that's feeding into, basically between that associated apparatus and that field device, really there shouldn't be any other devices other than your cabling and your interconnects, maybe marshalling boxes, junction boxes, and things like that.
Well, and to be 100% honest, there is a limit also on the barrier, An isolated barrier or a barrier has a certain parameter which is called which is the maximum voltage you can apply to that device. So for example, in case of GMI, they're all 250 volts. So it means that the power supply you're powering into an IS barrier shall not be bigger than 250 volts. Of course, it's 24 volt, but yes, but you know, so there are some limits also. Okay, let's move forward. We have some prepared questions, and then we'll look. How do I connect the safety ground of a Zener barrier? Well, you discussed this already, Bob, but here we go.
Yeah, that picture on the right-hand side. So a lot of people are, to understand that a little bit better, a lot of Zener barriers will actually be grounded. Obviously, you can see that they'll have typically some earth lugs or earth tabs or something like that to make a direct connection. But a lot of Zener barriers are actually designed to be mounted directly to a metallic DIN rail. And that DIN rail could be attached to a grounding terminal, which in turn is attached to the DIN rail. And then that's tied off. The key thing to remember there is that if you're mounting Zener barriers inside of a cabinet, and that cabinet is a metallic cabinet, we want to make sure that that DIN rail is isolated. So we don't want to, again, interfere with the normal system ground in that scenario. So that's really just the key thing to remember. If we are using Zener barriers and we're using that DIN rail for grounding, then we want to make sure that that DIN rail is isolated in some way, shape, or form from the enclosure itself.
Okay, next question. So, do we have to keep the IS and non-IS one separated from isolator or for barriers? That's a simple question.
Yes. Yeah. So there is a minimum segregation between IS and non-IS. And the minimum distance required is 50.
Please do not give it away because I prepare a poll for our game.
Sorry. So yes, there is a minimum distance.
Yeah, in fact, you know, so you have to keep a distance. I prepare a poll for it. Let's see if I can run it while I'm doing this and checking the presentation. So, okay, so guys, we had this during our six mistakes, typical mistakes in IS application. What is the minimum distance required between IS and non-IS? 50, 80, 40, 25 millimeters. Okay, while I do that, you run this poll. Let me see other questions. You got a lot of questions coming in. Do we have ICX Zone 2 certified power supply? Yes, we do, guys. You can look it up online. Presently, isolator combined with IO module on DCS, ESD, and then synchronization are required. Yes, isolators are typically IO card can be isolated. Some are not. But the isolation and IS isolation are two completely different stories. An isolator that is not intrinsically certified cannot be used instead of a barrier. So if you don't need isolation, you want to use a Zener barrier, that is fine, or you can double the isolation, but you do require a barrier. Okay, let's end the poll. Share result. Well, Bob, I'll let you comment.
Yeah, no, fantastic. No, that's 50 millimeters is the minimum distance. And typically, here's where people usually, again, one of our 6 common mistakes. If you go back, Paolo, or close that poll for a second.
Wait, let me try to get out of the poll because otherwise I cannot manage the presentation. In fact, whoops, okay.
I just shared it. So.
You shared it, sorry. Okay, I'm trying to move around the presentation. I show this as, you know, this is the right way, and this is not the right way.
Yeah, there we go. Okay. So you've changed this presentation up. So there we go.
Yeah, well, I told you to change it a little bit, you know.
There you go. So if you look at the picture on the right-hand side, that is, if you notice, there's a plastic partition on the coming down, and you see that there's some output from those various barriers that are going via barrier glands going into the field devices. These are mounted inside of an EXD box. And then obviously there's some sort of electrical device on the left-hand side, and that's powered. Now that partition there is to meet that 50 millimeter requirement. However, the problem is that they looped those cables and they dropped them down through the entries. So therefore we missed out our 50 mil segregation between the cables. So we have to make sure that we not only keep the devices separate by 50 millimeters, but the cables also need to be segregated by at least 50 millimeters, unless we're using some sort of shielded cable. That's generally pretty much a worldwide requirement. Armored cables, things like that, or shielded cables, we need to have segregation if we don't have some sort of shielding or armoring of our cables. So when you see on the very left-hand side that looping around, you know, service loops on the inside of a cabinet, that's a big no-no, because now all of a sudden we've defeated that 50 mil segregation. And that picture in the middle, again, when it came out from the factory, we had our blue terminals on the right-hand side, segregation. Our power terminals, looks like there was an earthing plate. There was also some earth terminals, which is separate. So probably one of those was our PE. One of those could have been just our clean earth. I'm not really sure which is which, but obviously it's all jumbled up, and we've missed out on our 50 mil separation. Okay, good.
Well, I keep looking at the question coming in, guys, and we are almost into an hour. Well, there was a question about Zener Barrier with a grounded sensor. You discussed this earlier, Bob. You know, you cannot use a grounded sensor because you create two paths for the fault core and to ground. So isolation in the field is required, minimum 500 volt, right?
Correct.
We have a live question here that you might want to look at, Bob, while I go forward, because it sounds complicated.
IEC, the 6100-5?
Yeah.
Question? Yeah, there's a question, and this is a great question. IEC 6100-5 does not recommend multiple isolated ground, i.e. separate ground for clean versus dirty protected ground.
I post the question so our guests can see it.
Oh, okay, you can do that. Fantastic.
Okay.
Well, I don't have the answer, but that is something I will look into. I do know within the -14 standard, it does say that we have to have a separate clean earth versus a dirty earth. But I do know that the 6100 standards for earthing and grounding are a lot more detailed. So I will take a look at that, and we will try to answer some of these questions offline or get those in a spreadsheet and send them back.
And we have your names, we have your email, so we'll get to you. So there was a couple of live questions that came, and they were and was a similar question during the presentation, during the registration. So it is, can I install a barrier in a classified area? And to expand to that question, well, we have a prepared and answer it live. Somebody asked if I need an IP66 enclosure, or do I need an XD enclosure?
Right. So to mount barriers, generally speaking, and again, you have to figure out what brand it is and what the rating is. But most barriers that you will find in the marketplace, including GMI's products, are actually suitable for output into a zone 0 area, but are actually designed to be installed into a zone 2. So they're actually dual marked, if you will. They'll actually be EXNA, or actually to the new marking requirements, I think it's EXEC. But basically, they can be mounted into a zone 2 as long as they're in a suitably approved EXN type enclosure, generally speaking. Now that's generals. Look at the specific wiring regs in your country to make sure. When we want to mount a barrier in a zone 1 area, however, we do basically at that point have to install it into either a flame-proof box, or in this case, a purged and pressurized enclosure, which could be like a PXB type purged pressurized system. So we could either do EXD in effect, and by the way, it's now going to be known EXDB, or an EXPXB type purge system to be able to mount those barriers located in a zone 1 area.
We have a question that I'll go back here to the wiring, but basically asking about shields. Where do we ground the shield? If I remember correctly, last time we had the same question. We said yeah, they can be grounded in the field or in the safe area, but as long as it's in a single location, correct, Bob?
Yeah, well, generally speaking, what we want to do is that any shields that we have that are going into the field device, typically we want, there's a couple ways of doing it. We can terminate them into unused terminals. That's probably the best way. We would take some insulation, typically some heat shrink tubing, and we would insulate that shield. You don't want to just snip it off. You want to actually leave it and then take it and then tie it into an unused terminal. And we want to connect it into the safe area. We want to run that shield all the way back into the safe area, and that would be tied into either earth or generally an earthing terminal located in the safe area all the way back.
All right, the next question is definitely for you, Bob. What do all the symbols mean in the EX marking? And since you are talking about this marking, you're also talking about different certification method, like we see here, EXIA, and you might want to elaborate on another question after, which is...
Yeah, so there is a question, does EXNA and EXIA are same for intrinsic safety applications? What's the difference between them? Well, actually, EXNA is non-arcing. It's a protection concept that's referenced in 60079-15, and EXIA is intrinsic safety suitable for zone 0. So EXNA, all the N-type concepts are all protection concepts that are only suitable for zone 2, where EXIA is suitable for zone 0, 1, and 2.
Yeah, so there's a big difference between the two.
There is.
Okay, why don't you go through a little bit about this marking for...
Sure. I'll go through this real quick. So on the left-hand side, under the bracket, you see directive marking. So the CE mark is conformity. The 0575, that's the number that's for the particular notified body, the testing lab, if you will, that did the certification. The hexagon EX is telling you it's compliance to the ATEX directive. You have to have that hexagon with the CE mark in order to be compliant to the ATEX directive. Then you have a Roman numeral 2, a number 1, and a G. So the Roman numeral 2 is equipment group, and that's basically telling us that that's a surface area application equipment group. So anything that's in above ground is going to be Roman numeral 2. Equipment category 1, that's basically telling us it's a double fault tolerant type product. But more or less, it equates to zone 0, and G is for gas applications. Then the standard marking is your EX mark, telling you it's explosion protected. In this case, using intrinsic safety with redundant fault tolerance, actually double fault tolerance, EXIA. And that's the difference between EXIA, IB, and IC is the fault tolerance. The gas group, Roman numeral 2C, which means it's good for all gas groups. And then T4, which is the T code, which is based upon a normal ambient of -20 to +40, unless the product has something above that, which I know GMI, we talked about that last time. I think your rating is actually to +70 degrees C. And then your EPL, which is your IECEX marking, which is now adopted under the ATEX directive, GA, which is basically telling us that our explosion protection level is for a gas atmosphere with an A. So it's either going to be...
Why don't you elaborate a little bit on that T4? Because I remember one of the latest registrant posed a question about T6, what that temperature means.
Right. So every piece of electrical equipment, generally speaking, is going to have a temperature code assigned to it. And that's basically what that T code stands for, is what is the relevant surface of that product when it's fully energized under a potential fault condition. How hot can it get under a normal ambient condition? So any EX piece of equipment out there, that if it doesn't have the temperature or the ambient rating on it, it will always be assumed at -20 to +40. So what that T4 is telling us, just hypothetically, if we didn't see any ambient marked on this product, let's just assume at +40 degrees C, a T4 marking is telling us that the relevant surface of that barrier will never exceed 135 degrees C under a fault condition.
Okay.
If it was marked T5, that would mean that that product would never exceed 100 degrees C. If it was marked T6, it would never exceed 85 degrees C. So in order selecting products, we have to understand a couple things. We have to understand the zone. We have to understand the gas groups. We have to understand the temperature codes. So that standard marking that IA is telling us it's good for zone 0, zone 1, and zone 2. The Roman numeral 2C is telling us it's good for all gas groups. And T4 means that that product can be used in any gas that are rated at T4, T3, T2, or T1. If we have a gas that's rated T5, that means that that gas has an auto ignition temperature of somewhere above 100 degrees C, and it would not, you could not use that product in an environment in which T5 was the requirement for the project, if that makes sense.
Yeah, because basically, you know, there's different ways to ignite the gas. You can have an electrical spark or arc, but also temperature. So if you have a hot spot on that field device, you know,
Right.
that which is, you know, they are calculated, and they say the maximum temperature reached is 70 degrees. Well, you must make sure that the gas comes in contact will not ignite at 70 degrees.
Right.
Right. Okay. Sorry, go ahead.
Yeah, there is one open question that I wanted to answer. We get these certified EXI junction boxes in the market.
Yeah, I was going back to here, you know, and say, okay, let's answer this question, because I am always, you know, get this confused. Do we need? So the question is, do we need EXI certified junction boxes or not?
So what it really boils down to is the standard says actually in dash 14 that if you have a single circuit, okay, when we're talking about a junction box, a single circuit, if we're following dash 14, the box actually just has to meet the impact resistance requirements of 60079 dash, I believe it's 0, and I believe that's all it states. Now, the moment that we actually have 2 or more circuits into that junction box, then the box actually has to meet the impact resistance requirements either of EXN, which is 4 joules impact, plus IP, I think it's IP 54 or greater, or if it's going into a zone 1, the impact resistant requirement goes up to 7 joules impact. Now, in reality, the question, this always does come up, does it really need to be a certified box? Well, in reality, it does need to be a certified box. It doesn't necessarily have to be an EXI box. It generally is an EXE enclosure. However, what they do require is that the box must have marked on it intrinsically safe circuits inside. There must be a blue label on it saying intrinsically safe circuits on the inside. So in reality, is there really any difference between a non-EXE box and a good quality junction box that's IP 64, 65, 66? Maybe not, but the standard actually does require you to use a certified box for more than one.
Well, I thought differently, but you are the expert. So let's see, we are into 1 hour. It's kind of late for you. We had a live question that, if I can pull it up again, he said, where did I put this question? You guys put too many questions today.
Well, there's a good question, a question about zones.
Yeah, there's a question about, okay, you can answer that.
Yeah, why has the IEC zone 0 risk 100% of the time and zone risk during operation? The NEC only has class 1 div 1 to both cases. That's a great question. I don't really have a good answer to it, but basically going way back, the National Electric Code, we basically did not adopt the zone concept. And in reality, when we did adopt the zone concept, we basically did adopt zone 0, zone 1, and zone 2. But in reality, what we say is that a product that's suitable for div 1 is actually in many cases suitable for zone 1. But why we actually, in the United States, we have 2 divisions, and the international world has 3 zones, that goes way back. and I really don't know the answer.
For sure, you know, zone zero is a concept that is more European. And I personally believe, you know, we have installations here in Europe. They are very, very, how do we say, very, very close to cities. They're in the cities.
Sure.
You know, the danger there, it's actually higher than putting a refinery somewhere out, you know, in Dakota or downtown German city, you know. So I think that is where attention to safety may be a little bit higher, but why, we don't really know. So there was a question live that said, in IS loop application, can we connect TVS, transient voltage suppressor, we call it SPDs, and between ground, chassis ground, what are the disadvantages and advantages? We had also a register question that says, can SPD be replace the isolators? How about grounding of the same? Is there any grounding issues? So we prepare an answer here. We are not, I want to be 100% honest, I don't know about you, Bob. I'm not a great expert of SPD, but we got our technical team to prepare an answer. And basically, SPDs are designed, or TVS as our guest calls them, are designed to protect from field to the control room. So, you know, an accident happening, some lightning going into the field, the wiring, the high energy is coming back into the control room. Now, an IS barrier, at the very opposite, is protecting the other way around. From the control room to the...
It is to an extent, although you could say that an SPD, in effect, is also protecting against those large surges that could come into your control panel, and that control panel, if left unchecked, would come down that cascading system and eventually wind up at the ISB. So you can look at SPDs in a couple different ways, but they, in effect, I mean, they have MOVs typically on the inside of TVSSs, and they absorb the energy, and they also shunt the energy, just very similar to ISBs, especially galvanically, not galvanically isolated, but Zener diode type. So they are designed to absorb the lightning strike and then dissipate that energy to ground in a very rapid fashion.
For what matters to our webinar here, you know, what is important to understand is both need to be certified. So your SPD or TVS that you are installing into hazardous location or interfacing an hazardous location, so next to a barrier, must also be certified for the same use. And the grounding must be independent from your, if you're using a Zener barrier, you cannot ground the Zener barrier to the same ground you ground in your SPD, correct, Bob?
Correct. Correct.
As we discussed earlier. And now the question was discussing about grounding problem, and I understand that the way to avoid that for all the SPD is to unipotential connecting these grounds. So they have to be equipotential, the bonding. There's a way to connect your SPD to the same ground, make the same ground equipotential, so then you avoid any loop issues. Now, we are way into our time. It's kind of late for you, but you know, we had a question about seal. Should I worry about seal certification for an IS barrier? I believe, you know, it's not a requirement of the standard, but you know,
yeah,
it's not a bad idea, right, Bob?
It's not a bad idea. And here's, I guess, you know, the whole idea behind SIL is you basically now have qualified the, and I apologize, it is kind of late, but I'm just trying to think of the word. You more or less...
It's very late for you. And let's see if our guests are still with us. Well, you know, we have still a lot of participants with us, so let's go for a few more minutes and then we cut it out.
Okay, our SIL rating, basically what we're trying to do here, or we now have defined failures, if you will. We know how reliable our product is going to be since we've independently tested it and verified it by a third party. So again, you've got a defined failure data. So this really what it means to me, if you will, again, it's not a requirement by any stretch unless you're using barriers in a SIL loop or something like that. But just to use a SIL rated product. Really all it means is that that product has been certified, that you know the failure rate and that it's going to be extremely reliable. That's really what you're getting by buying a product that actually has a SIL rating. The reliability is known, and generally speaking, because in order to get a SIL rating on, say, for example, an intrinsically safe barrier, you have to go back through each and every component, traceability, and then you have to find out the failure rates of all of those components. You have to make those calculations. And so therefore, when you put that in the field, you have a pretty good understanding that this product is going to survive for an extended period of time. That's basically the advantage of using SIL.
Safety for safety. All right. Well, we can skip this. You know, there was a question about if isolated barriers are available for to condition any type of signal. Yes and no. There are many applications. Some are specific to Zener barrier, but there are a lot of isolated barriers in the market for many type of signals, from AI, AO, DI, DO, universal, and many special applications. You can look it up online, you know, from our website, what we offer. This is again a question about trying to summarize the differences between isolator and Zener barrier, specific to the question came in specifically for high current. There is always a solution. Sometimes you might need a Zener barrier because there is not an isolated barrier available. It is rare, honestly. You know, yesterday we had this long discussion with this customer again, and they were using many Zener barriers, and they gave us all the model numbers. By the way, you know, of a manufacturer that is discontinuing Zener barrier, because majority of the market is disappearing for Zener barrier. So, and we could not find an application that would not solvable with an isolated barrier. But we have another customer here in Italy. It's a big customer who has many isolated barrier uses from GMI, but it's also using a specific Zener barrier. Now I don't remember the application, but there is no isolated barrier for it. Well, we are designing one, so eventually we'll have that also. In conclusion, we have many times you guys register, you ask about other webinars. Well, we have a lot of webinars. Just look them up online, okay? We have a schedule. This constantly updated. We are also going into August. It's our typically vacation time, but we're still doing webinars. So let me conclude with a poll. Let me know, guys, let us know how we did. Me, especially Bob, because, you know, he is the one who's doing the greatest job here. I'm just, we have some more questions live, but I don't know if we have time for it. We will try to get to the answer.
Yeah,
we cannot answer online today. We will answer them, you know, via mail.
Yeah, what we'll do, we'll send out, again, you'll get a copy of the presentation. We'll put together some of the questions that have been asked and the answers. We'll try to get that to you all. Anybody who's registered, we'll get that to you here pretty quickly. Give us a couple days.
Okay, great. So most of you guys think we did very great, and let me show it to you so you can see. Thank you very much. Thank you for participating. Thank you for your attention. I see you still there. Let me stop the presentation here. Let me close this box. Okay, Bob. Well, good evening to you. Actually, good night. And the same to you guys. Thank you for participating. And see you soon.
Sounds great. Thank you, Paulo. And thank you, everybody.
Thank you. Bye-bye. Cheers.
Cheers.